Okay. Oh, hi everybody. We're going to quickly finish up the section on obel summation. There's not much more to say. I'm not going to do the proof in this lecture for obel summation. I may make a short video later for the proof. It's not a very long proof, and if you're familiar with the proof of integration by parts, it's not all that different. You just have to replace the word derivative with finite difference in a couple of key places. So where we ended last time was using obel summation to prove this asymptotic formula for the partial harmonic sum. We found this differentiable main term, and we found a pretty small error term, this big O of 1 error term. And if you started looking at the problem sets, there are quite a few problems in the obel summation section which are similar to this. They're basically practice using obel summation to figure out, well, how does this partial sum grow? How small can we make the error? Things like that. And so the last thing from this section that I wanted to go through is sort of a culmination of the things we talked about yesterday. So when we were on CoCalc, we graphed some pictures of functions. We graphed the divisor function and the sum over the divisor function, and we graphed x log x, and we noted how those were pretty close together. And so now we've actually built up all of the tools necessary in order to prove this. And so that's what I'm going to go through here. And there's a few problems that use these kinds of ideas in the problem set as well. All right. So just to recall, divisor function. Oh man, I might have to restart this app. This happens sometimes. All right. Hold on a second, everybody. Bring that back in just a second. Okay.
I can see it.
Great. Yeah, sorry about that. Sometimes it does that where it doesn't display the things that I've written for more than a second. Okay. So the divisor function is the number of positive divisors of n. That's how we define the function. And we can write this function in a couple of different ways, which will be useful to us. We could write it as the sum over all the divisors of n of 1. So for every divisor, you add a 1 to this value. Another way to write it is we could write it as a sum over 1 of the number of ways to factor the integer n into a product of two other positive integers. And the reason that we can do this is because the definition of d dividing n, that actually means n is equal to d times a. Or some other positive integer a. Writing the sum like this is going to be convenient for actually figuring out and evaluating what's going on with this partial sum. So we set up the partial sum for n less than or equal to x of the divisor function. So we plug in, we know that this is the sum over all the ways you can factor n as a product of two integers of 1. And now what we can say, if we look at these two sums, the role that n plays is not significant. We're saying, oh, you look at all n less than or equal to x, but then you look at all the ways you can factor n as a product of two numbers. So what we could say is that this is really the same thing as the sum over the products of any two integers that are less than or equal to x of 1. Because all I've done is I said, well, n was written as d times a, so I can remove the letter n from this notation. And so now what we can do is we can choose an order to sum over these two possible numbers, whether we sum over the different values of d first or the different values of a first. So I'll put the sum over d on the outside. So certainly, if d times a is less than or equal to x, that can only occur if d itself was less than or equal to x, because these are all integers. And now I need a sum over a values that also satisfy this inequality. Well, in order for d times a to be less than or equal to x, that's the same thing as a being less than or equal to x divided by d of 1. So now this is all the same thing. What I've been doing here is I've been re-indexing sums. I've been switching the orders of summation. So I moved the sum over d all the way to the outside. And then we've got this other sum on the inside here. So what's so useful about this? Well, what's useful about this is that the inside sum, we actually know what this is. Because it's a sum over the integers a that are less than or equal to something else. That's actually the floor function. So that's something that we have already computed from yesterday. So I'm going to run out of space on this page. So what I'll do is throw on an extra page next to it, and we'll continue the argument on the next page. So now we have the sum of the divisor functions is the same thing as the sum of these floor functions. This is more convenient for us because we already know how to approximate the floor function with a differentiable function and with a very small error term. So I'll jump to the next slide. I'll rewrite the step we were on. So we had already shown this. So next, we know the floor function is equal to, well, it's approximately the thing that's inside, where the error is big O of 1. All right. So now all that's left is to take a sum over d less than or equal to x of these pieces. So the first piece, well, this x in the numerator, we can factor that out. X times the sum of over d less than or equal to x of 1 over d. And then for the big O, the sum of big O of 1 is the same thing as big O of the sum of 1. This was one of the exercises on properties of big O notation from yesterday. Now we can use the fact that the very last thing we proved last time was that this partial harmonic series, we also know how to approximate this function. This is log x plus big O of 1. And we know that the sum of a bunch of 1s is the floor function of x. So if we distribute this as x, we get that the sum of the divisor function is equal to, well, this x log x function, which is what we expected from our co-calc work, plus an error term of the size of one of these two functions. And so then the very last thing to say to make sure we get the error term that the lemma says is that we know the floor function is less than or equal to x. So, well, floor function of x is already big O of x. So really, the second error term can fall into the first error term. And we'll be all done. So what Abel summation does, we didn't really use Abel summation in this work, in the proof of this theorem. What Abel summation really does for us is it allows us to find the main terms and error terms of a lot of base functions, like the harmonic series. That showed up in this computation. We were able to compute the harmonic series using Abel summation last time. So that's where Abel summation is the most useful in the context of analytic number theory. It allows you to find the asymptotic main terms as differentiable functions for lots of very basic, sort of differentiable looking functions. And then the next step after that would be putting those together in order to come up with asymptotic main terms for other arithmetic functions that have more number theoretic information contained in them. All right. That is the end of this section. That wasn't very long, so I don't think I'm going to stop for questions just yet. We'll keep going into the next section, and we'll stop for questions a little bit later. The next section is about the Mobius function. And so if you've taken a course on analytic number theory, possibly if you've taken a course on elementary number theory, you've seen this function before, but I want to make sure to cover all the bases. So we're going to talk about this function. At first glance, this is just a really weird looking arithmetic function. Here's the definition of the Mobius function. If n is a product of distinct primes, so it's not divisible by any squares, then the Mobius function is -1 by the power of the number of primes. Otherwise, the Mobius function is 0. So if you plug in a square function or anything divisible by p squared, you get a 0 here. So a couple of example values. 1, that's not divisible by any squares. It's a product of 0 primes, technically. So that's -1 to the 0, which is 1. 2 is a prime, so that's a product of exactly 1 prime. So it's -1 to the first power. 3 is also a prime, so for the same reason, we get -1. 4 is a perfect square. So the Mobius function of 4 is equal to 0. And etc. The next number where the Mobius function is equal to 1 is 6, because 6 is divisible by 2 distinct primes, so it's -1 squared. And so I've put on this page a pretty useful lemma, and we'll talk about why this is useful in a minute. But this tells you that even though this Mobius function, the definition looks a little weird, it obeys this really nice rule that if you take a sum over all the divisors of n of the values of the Mobius function, it's almost always going to be 0, except when n equals 1, because if n equals 1, you're only adding up one term. There's nothing to cancel out with it. So write down the proof. If n equals 1, again, this is just a sum of a single term. It's mu of 1. There's nothing to cancel out. That's just equal to 1. Otherwise, let's say that n is not 1, so it's a product of powers of primes. Well, if we take a sum over all divisors of n, we know that the Mobius function is only non-zero if the number we're plugging in is not divisible by any squares. So if n is a product of these primes, maybe I should index them, I equals 1 up to k, we can list out the possible choices for the divisors that give you non-zero values of the Mobius function. 1 is a divisor of every number. That's a possible choice. Each of the individual primes, those aren't divisible by any squares, and they're divisors of n. Those are all possible choices. We can have a product of 2 primes. If they're distinct primes, we know that that product still divides n, and it's not divisible by any squares. That's a choice. And we could do the product of 3 distinct primes dividing n, of 4 distinct primes dividing n, all the way up until, oh, I'm going to run out of room. The product of all distinct primes dividing n. And now, because we've separated it based off of how many primes are dividing the divisor, we can actually write down exactly what the Mobius function is in each of these cases. The Mobius function of 1 is 1. The Mobius function of a prime is -1. And there are exactly k choices for a prime dividing the Mobius function. So this sum has length k. The Mobius function of a product of 2 distinct primes is -1 squared. And the number of choices for 2 distinct primes dividing n, well, that's like choosing 2 indices out of the total k indices, is k choose 2. And this pattern's going to repeat until we get down to -1 to the k, which is the value of this last Mobius function. And we might start recognizing, well, k, that's the same thing as k choose 1. We could write a k choose k right here. That's times 1. 1 here is the same thing as k choose 0. This exactly matches the decomposition that's found in the binomial theorem. So the binomial theorem tells us that this sum of binomial coefficients times powers of -1 is equal to -1 plus 1 all raised to the power of k. But then you just have a -1 plus 1 inside some parentheses. That's equal to 0. All right. That's kind of neat. Maybe that by itself isn't necessarily convincing to you that the Mobius function is an interesting function if you haven't seen it before. And so that's why I'm going to show you this theorem. Mobius inversion is kind of the big reason why we care about the Mobius function so much. If you write one function as the sum over divisors of n of another function, you can invert that expression using the Mobius function, using this expression right here. Before we do this proof, I'll just write down an example of one of these formulas we can produce. We were just talking about how the divisor function is the sum over divisors of n of 1. Well, Mobius inversion says that we can flip the roles of those two functions. So 1, the function which is identically 1, is equal to the sum over divisors of n of mu of d times the divisor function of n over d. And I'm starting to regret using d, so I'm going to use the other notation, sigma 0. It means the same thing. Mobius inversion gives you this sort of inverted formula, which is maybe not obvious from the definition of the sum of positive divisors function. This plays a lot of important roles in analytic number theory, way too many roles for us to discuss in this mini course. After we prove this theorem, we're going to use some of the ideas in Mobius inversion. It'll be hiding under the surface to do a very basic sieve to count square free numbers. All right. Let's do this proof real quick first. So we are taking this sum, and we want to show that this sum is equal to g of n. So how am I going to do that? Well, first, I'm going to rewrite the sum. Instead of saying as a sum over d dividing n, I'll write it as a sum of factorizations of n into a product of two positive integers. That way, n over d is just written as a. It's a little bit cleaner this way. And so the reason why we want it to be written like this is f over a is very easy to write by assumption as a sum of values of g. So this is exactly this formula up here. So that's the one thing we know about this function. It's the one thing we're assuming. All right. Well, let's do that same thing again. Instead of writing a sum over divisors of a, let's write it as a number of ways that you can factor a as a product of two integers, like that. And now the a doesn't play a role in the sum anymore. There's no a's on the inside. There's an a down here. We have n equals d times a, but then we immediately say, oh, sum over all the possible ways to factor a as b times c. So this is the same thing as summing over the number of ways to factor n into three integers of the product of these two functions. All right. Then what we'll do, we want to, basically we're going to try to undo this all in the opposite way. So what we started with was basically the g function on the inside sum. So let's try to reverse the orders of the summations and put the mu function in the inside sum. Well, if we want the mu function in the inside sum, then g should be on the outside. So the very outside should be the sum over the possible values of b, g of b, and then times the sum of everything remaining. So d times c is equal to n divided by b of mu of d. All right. Well, this d times c sort of running out of space on this page, so I'll throw another page in after this. Saying that n over b can be, you're summing over the possible ways to write n over b as a product of two integers. That's the same thing as a sum over positive divisors. We're going in the backwards direction now. So we'll go to the next page. I will rewrite where we were. We had the sum over b divides n, g of b, sum over the factorizations of n over b into two positive integers, the Mobius function. So then we say, well, summing over factorizations into two positive integers is the same thing as summing over divisors. But now, this is exactly the sum over divisors of some number of the Mobius function. We know that this is equal to 1 if n over b equals 1, and 0 if n over b does not equal 1. So what this tells us is this big term in the parentheses is 0 for most of the values of b. Everything except the one special value, b equals n. So this is a bunch of zeros plus g of n times 1, which is exactly g of n, which is what we were looking for. That's the Mobius inversion. We're not going to do too much with Mobius inversion itself in this mini course. There are a couple of exercises about it in the problem set. And if you read a book on analytic number theory or take a course on analytic number theory, you'll use it a lot more in other contexts than we're doing in this course. But we'll probably use more the individual lemma, what I have right here in red, that if you sum over divisors of some number of the Mobius function evaluated on a divisor, that cancels out unless you're summing over the divisors of 1. All right. So what we're going to do, we're going to use the ideas of this Mobius function to talk about a sieve of square-free numbers. So again, I've put up this big box of all numbers between 1 and 100, and we're going to sieve out in order to find the square-free numbers. But we're going to do a little bit more than we did for the sieve of Eratosthenes yesterday during the introductory section. We're not only going to color in the square-free numbers in this box green, but we're actually going to count them. We're going to answer the question, how many square-free numbers are there less than or equal to x? That's some function of x. It's like a smoothed out characteristic function, and we'll be able to say, oh, this function is approximately some differentiable function, and we'll be able to give the error. So I'll show you the result on the next slide, but before we see that and think about the answer in too much detail, I want to actually go through the sieve on this slide. So we'll start using floor function of x. That's just, we start with everything, all the numbers here. Okay, so going from the bottom up, well, 1 is square free. We get that for free. Other numbers being divisible by 1 isn't going to stop them from being square free. 1 is kind of special. 2 is square free. It's small enough that it's not divisible by any primes. Okay, but we know that perfect squares, the next perfect square is 4. So basically 2 and 3. I guess I can keep going. 2 and 3, those are both square free. Then we get to 4. That's a perfect square. It's not square free, so I can remove it. And everything that's divisible by 4 is also not square free. So 4, 8, 12, 16, 20, 24, 28, etc. All of these numbers are not square free because they're divisible by 4. So what did we just do? We removed all the numbers below x that are divisible by 4. So we subtracted the number of things below x divisible by 4, which is the floor function of x divided by 4. So that's the second step of our sieve, really. We started going from the bottom up. We found the first problem value that's not square free, and then every multiple of that would also not be square free. So we had to remove all of those. Okay, let's keep going. 5 is square free. 6 is square free. 7 is square free. 9 is not square free. 9 is a perfect square. Okay, now we have to do the same thing. we remove 9, we have to remove all multiples of 9, because if they're divisible by 9, they're not square free anymore. These are a bunch of multiples of 9, also 90 and 99. So we had to remove x divided by 9, approximately, numbers, because that's how many numbers there are below x that are divisible by 9. All right, before we keep going, we have to stop and think for a second. 36 and 72, they're a little darker because I've removed them twice. So if we're actually trying to count the number of square-free numbers, and I look at what I've written in my equation on the left-hand side here, I've actually subtracted a 1 for 36 2 times, and I've subtracted a 1 for 72 2 times. So right now, all the green numbers are counted once. All the numbers that aren't shaded at all are counted once. And 36 and 72 are counted -1 times. That's not good. We've over-removed those numbers. So we have to be careful about that and be sure to add back in the extra copies to make sure we don't get a bunch of extra minus signs throwing off our computation. And so the set of numbers that we overcounted are the numbers that are divisible by both 4 and 9. Or in other words, all the numbers divisible by 36 had been over-removed. So if I add back in the floor function of x divided by 36, that will undo the fact that we had overcounted those numbers. Okay. So we keep going. 10 square free, 11, 13 through 15. All these numbers are going to be square free up until we get to 25. So 25 is 5 squared. We have to remove all the numbers divisible by 5 squared. So let's do that. So that's 25, 50, 75, and 100. Well, 100 got double counted. So in order to make sure that we're not subtracting too many ones for the 100, we'll have to add back in x over 100. And the reason for that is because 100 is divisible by 2 squares. That's why we overcounted it. We had to add that back in to make sure we don't overcount. And then we keep going all the way up until the next square. The next square is 36, but the multiples of 36 are already removed because 36 is a multiple of 4. So we keep going up to until the next square. The next square is 49. And then we have to remove all multiples of 49. So I'll throw this in up here. This is minus x over 7 squared. The only other multiple of 49 that's below 100 is 98. And we keep going. The next square is 64, but 64 and all of its multiples are already removed because those are divisible by 4. Keep going. The next square is 80. The next square is 81. But 81 and all of its multiples are already removed because those are multiples of 9. And then after 81, the next square is actually 100. But 100 and all of its multiples are already removed because those are multiples of 4. And so what we've done is we've now filled out all the green numbers on this page are all the square-free numbers below 100. But we've done more than that. We've actually kept track, making sure we didn't overcount, so that we have a formula that tells us how many square-free numbers there are when x is equal to 100, or if we pick a different number for x. This process is called inclusion-exclusion. It's a type of sieve, also sometimes referred to as a type of combinatorial argument for counting things, because what we did, we started with all the numbers, we excluded a bunch of bad sets of numbers, the numbers divisible by the primes squared, but then those overlapped a little bit, so we overcounted the things we were trying to exclude. So we had to re-include the things that got double counted. Now, 100 numbers is too small to see the next behavior, but actually when we re-included the things that got double counted, we over-included something. So one number that we would have over-included would be 900. 2 squared times 3 squared times 5 squared is 900. It shows up right here. It's subtracted here, here, and here. It's added here, here, and in one overlap that we didn't write down, which is this one. So what have we got? It shows up once, removed 3 times, added back in 3 times. So adding those all up, -3 and +3 cancel out. We're still counting 900 with what I have written on the board right now. But 900 is divisible by squares. So we once again have to exclude the overcounted number. And etc. for all numbers that are divisible by 3 primes squared. And then we would have over-removed numbers divisible by 4 primes, etc. So putting all of this together, following along with this pattern, we've got a formula for counting square-free numbers less than or equal to x. It's a sum of the floor function of x over d, where let's look, d, whatever this number is, if we look at all these floor functions, d is, well, it's a perfect square, but it's only divisible by primes squared. It's not divisible by any extra primes. And out front is plus or minus signs. So what I'll do is I'll say, we know d has to be a perfect square. It only shows up now if d is square free, since I put this square here. And it alternates signs. If d is divisible by a single prime, you get a -1. If d is divisible by 2 primes, you get a +1. If d is divisible by 3 primes, you get a -1, etc. That's the same pattern as the Mobius function. And so what we've done with this argument is we've now found this formula for the number of square-free integers below x. And this is an exact formula. All right. So now what we're going to do is we're going to use this formula to actually compute a differentiable main term and an error term for the number of square-free integers below x. So I'll rewrite this on the next slide, and on the next slide, we'll see what the formula actually is. I have it in a box. Number of square-free numbers less than or equal to x is equal to this big summation times x plus big O of the square root of x. Some of you might recognize this big summation. It's a convergent sum that converges to 6 over pi squared. Showing that this converges to 6 over pi squared it's neat, but it's not short. So I'm not going to do it on the board for you. This is related to Basil's problem if you want to read some more about it. So, what's the proof? Well, we know from the previous slide that the number of square-free integers less than or equal to x is given exactly by this sum. So somehow we want to take this sum and show that it's the same thing as this constant times x plus big O of the square root of x. the first thing that we'll notice is the sum that we came up with on the previous slide. It's not an infinite sum. The floor function is equal to 0 whenever the thing you're plugging into the floor function is smaller than 1. So if d is bigger than the square root of x, then this floor function is just equal to 0. It goes away completely. So we don't need to think of this as an infinite sum. We can really say, oh, this is the same thing as the finite sum just over d less than or equal to the square root of x, like that. That's important because if we write it out as an infinite sum, we have to be a little bit careful on the next step. So on the next step, take the floor function and we say, oh, it's equal to whatever's on the inside plus big O of 1, like that. And now let's distribute the summation. This is sum over d less than or equal to square root of x, u of d over d squared times x plus big O of the sum of d less than or equal to square root of x of 1. This is why it was important to limit our summation to a finite sum. Otherwise, in this big O term here, we would have a sum over all integers d of 1. That's a divergent sum. It would completely go to infinity, no matter what x is. And then we would have big O of infinity, which is just huge. It's bigger than everything possible. We wouldn't be able to say anything substantial. So knowing that this sum is secretly a finite sum is a very important step to this problem. All right. So we're getting pretty close to seeing the result in this theorem. We see the main term looks kind of similar to this, except that we have a bounded sum right here instead of an infinite sum. The error term looks pretty close to our error term, and in fact, we can say that it does belong to the error term because this is big O of the floor of square root of x, which is definitely smaller than square root of x. So at least the error term matches up. But how are we going to take care of this main term? So this is a nice little trick that'll be useful on some of your homework problems. We're going to go over to the next slide in order to do this trick. So I'll rewrite the main term on the next slide, and I'll show that this main term is equal to this term plus big O of the square root of x again. So add a page. There we go. So here is the function we're looking at. So the trick is I'm going to write this as the sum over all d minus the sum over d which are bigger than the square root of x, all times x. So that's fine. We just took a finite sum, said, oh, this is like the infinite sum where we remove the tail. Now, technically, we should be a little careful. This only makes sense if the infinite sum converges. Otherwise, what we've done is we've written a finite number, a function of x, as infinity minus infinity, which is not good. Infinity minus infinity is indeterminate. But we can say that this sum converges because we know the Mobius function, it's only ever equal to 1 minus 1 or 0. So we can use the comparison theorem on series to compare it to the sum of 1 over d squared. This converges by comparison. With this sum. P series with p equals 2. So we know we can write it like this. So what we have is this convergent series times x, which is the main term that we were looking for, minus this series for large D, the tail series, times x. So to complete the proof, we would also have to show that this tail series belongs to the error term. So this is another place where Abel summation is going to be useful for us. So let's look at this series. And since we're trying to show that this belongs to the error term, we don't need to worry about the exact value of the series. We can just look at an upper bound. I'll bound it above by the tail of the P series. And then what I'll do, I'll write this in red so it stands out a little bit. We can do Abel summation if the upper bound is infinity. Just like you would do any other improper integral. You have to write it as a limit, and as long as the limits exist, then your corresponding integrals and your corresponding summation exists. So we know this would be like d between square root of x and y, and then take a limit as y tends to infinity. I'm going to skip writing it out as y. Abel summation will tell us, well, I'll write this in green over here. We'll use a sequence of ones. The partial sum of ones is the floor function of t. Our differentiable function is 1 over t squared. So f prime of t is negative 2 over t cubed dt. So in Abel summation, we get f times capital A. That's floor of t divided by t squared, running from square root of x to infinity, where we know that that really means there's a limit right there. Then minus the integral from square root of x to infinity of the floor function of t times negative 2 over t cubed dt. All right, so here we've got Abel summation again. Okay. So, what we can do here is pretty much the same as what we did for Abel summation before. We know how to approximate the floor function of t. The floor function of t is, we'll do this in blue. T plus big O of 1. But I'm actually going to skip a few steps to save myself some space. If I keep everything in absolute values, like this, then I can use the comparison that just says floor function of t is less than or equal to t. So in the limit, we'll have upper bounds that look like this plus this. getting rid of the floor function of t by bounding it above by one copy of t, essentially saying that you're getting rid of one copy of t on both of these denominators. 1 over t, if you take the limit as it goes to infinity, that gives you 0. Plug in the square root of x, you get 1 over square root of x. Integral of 1 over t squared is minus 1 over t again. So you once again have 1 over t running between square root of x and infinity. So it's convergent because the limit as t goes to infinity of 1 over t is 0. And then the lower bound is, again, a 1 over square root of x, or in this case, 2 over square root of x. So up to a constant multiple, this is bounded above by the square root of x. So this bound right here applies to this series. So we found this series is bounded above by a constant multiple of 1 over root x. So if we multiply it by x, the whole thing is big O of x divided by square root of x, which is just big O of square root of x, which is the error term we wanted from the previous slide. This big O of square root of x right here. Okay. And oh, I guess I'm mostly out of time. So we won't start the next section.
Yeah, like 1 minute, or are you done?
I'm at the next section. I might as well wait. The next section is about prime numbers. Change gears a little bit. So you'll have something to look forward to. You use some of the terminology that Alvaro talked about today. But yeah, now here's a good place to stop if I only have a minute left.